Alright, in this chapter, chapter number 8, we'll discuss the properties of gases. In general, molecules that have 5 or fewer atoms from the first two periods of the periodic table, will be gases at room temperature. And in addition, this list here are also gases at room temperature. They include hydrogen, nitrogen, oxygen, fluorine, and chlorine. And they're represented by the subscript 2. That's because all of these are what are called diatomic atoms. So when they're found naturally, it's rare that you find them by themselves with one atom. They're always found or in a pair of two. That's why it's H2, not just H, or N2, not just N. That's how they naturally are found. Right, oxides of the nonmetals, the upper right corner of the periodic table, will also be gases at room temperature. They include carbon monoxide, carbon dioxide, nitrogen monoxide, NO2, SO2, SO3. And also the noble gases, the elements that are very, very stable on the far right edge of the periodic table. All right, now move on to the kinetic molecular theory. A gas will consist of very small particles that move randomly but move very, very quickly with a lot of velocity. These will also have very small attractive forces between each other. Sometimes they'll even have repulsion forces with each other. And they will occupy a much larger space than what the molecules have just by themselves. And here's what I mean by that. If you look at this image here, these circles represent the atoms whizzing around rapidly to form the gas, but the entire gas will take up the entire container. But if you were to add up just the size of each individual atom, much, much smaller amount of space than what the gas will give you because of the motion of the particles all over the container. All right, these particles that are found in gases are in constant motion and will move rapidly in straight lines. And they have a Kelvin temperature that is proportionate to their average kinetic energy of the molecule. Our gases are described in terms of four basic properties: pressure, volume, temperature, and amount. You'll see how they're represented here. Pressure, capital P; volume, capital V; temperature, capital T; and amount, lowercase n. Now, here are those properties and their definitions, and what units are used to represent their measurements. For pressure, that's the force that is exerted by the gas against the walls of its container. There are multiple units of measure that you can use for pressure. Atmosphere, which is represented by ATM. Millimeters of mercury, mm for millimeters, and Hg, the elemental symbol for mercury. Torr, the actual word torr, and then pascals, pa. Any of these units can be used to represent pressure. Volume, of course, the space occupied by that gas, can be measured in liters or milliliters, so capital L or ml. Temperature, the determining factor of the kinetic energy and the rate of motion of all the particles in the gas, can be measured in degrees Celsius or in Kelvin. And for the amount, of course, the quantity of gas that's present in the container can be represented by grams or moles. When it comes to the amount and the temperature of gases, those measurements are required to complete the gas law problems that we'll discuss here in a few minutes. If you don't have those measured, or if you're using the wrong unit, you'll get the equation wrong. So it's very important that you keep track of these units and use them correctly. Alright, first we'll discuss volume. Of course, the volume of the gas is the shape of the container that gas occupies. It will be represented by either milliliters or liters. Alright, the volume of a gas will increase as the temperature increases, as long as there is a constant pressure. There's a direct connection between volume and temperature. Alright, speaking of temperature, the temperature of the gas is the average kinetic energy of the molecules, and will be measured in Kelvin, not Celsius, but usually on the Kelvin scale. When that temperature of the gas goes down, the molecules have fewer collisions. There's less energy there. When that temperature goes up, that means there's more energy there, so there's going to be more collisions between the particles. Pressure. Pressure is the measure of the gas-particle collisions on the sides of the container, and measured in units such as millimeters of mercury, torr, atmospheres, pascals or kilopascals, or even psi, pounds per square inch. For this picture here, the atmospheric pressure is the pressure of the atmosphere pushing down on the top of this person's head. A barometer is used to measure pressure. Anything that ends in the ending meter is a reference to being measured, or being measured by, and baro is a reference to pressure. So a barometer will measure the pressure exerted by the gases in the atmosphere, and it's indicated by the height in millimeters of the liquid mercury. So what you have here in this image, a small container filled with liquid mercury. The gases of the atmosphere will push down on this liquid. That will cause the liquid mercury to rise up exactly a height of 760 millimeters. So that's why this is referenced as millimeters of mercury. It is literally talking about a specific height of a element. So millimeters of mercury. And these three values here are all equivalent. So 760 millimeters of mercury is exactly the same value as 1 atmosphere, which is exactly the same thing as 760 torrs. So all three of these represent exactly the same value. The only difference is using 3 different scales. So being able to convert from one unit to the other is critically important when you're given sample problems using the gas laws, which we'll go over in a few minutes. If you use the wrong scale, you won't be able to use the formulas correctly and you won't get the right answer. Alright, atmospheric pressure is the pressure exerted by the column of air on top of the atmosphere onto the surface of the Earth. And this will decrease as you go higher in altitude. So the standard measure of atmospheric pressure is 1 atmosphere, or 1 atm. So that's at sea level. Let's say at this water level here. As you go up to the top of this mountain here, the pressure will get less and less and less. So at the top of this mountain, it is 70% of normal atmospheric pressure. So instead of being 760, it's now 530 millimeters of mercury, 0.7 atmospheres. So the higher you go, less pressure. Alright, next we'll talk about the relationship between volume and pressure, also known as the Boyle's law. Now the relationship between the two is known as an inverse relationship. What that means is when one goes up, the other one goes down. They are inversely related. And here's a good way to think of that, or a common example of a way to think of this, is how you breathe with your lungs. If you take a deep breath in, the volume of your lungs and your chest increases. But when that volume increases, that causes the pressure to go down. That's how air gets forced into your lungs. And the exact opposite happens when you exhale. When you breathe out, your lung volume will decrease, which causes the pressure to increase. So air gets forced out of your lung. Alright, and here's a graphic to illustrate that. Of course, the pressure of a gas inversely related to the volume. When the temperature is constant, that's a key component of Boyle's law. The temperature must be a constant value. So this container, you have a volume of 4 liters, and the pressure is 1 atmosphere. When the volume goes down, the pressure now goes up, because you have a much smaller space for the same amount of volume. So the pressure has to go up to correspond to that decrease. So inversely related. Volume went down, pressure goes up. And here's the equation that's used to represent this. P1 V1 equals P2 V2. And when you see numbers like this, 1 and 2 in equations, 1 is always a reference to the initial setting or the initial reading or the initial value, and then 2 always represents the final value. So the way you look at this equation is the initial pressure multiplied by the initial volume is equal to the final pressure multiplied by the final volume. And the way you'll see questions referencing this equation, you'll be given 3 of these 4 values, and you need to solve for the 4th one. And we'll go over an example of that here next. Alright, here's a typical way a Boyle's law question would be asked. If I have 5.6 liters of a gas in a piston at a pressure of 1.5 atmospheres and compress the gas until its volume is 4.8 liters, what will the new pressure inside the piston be? So going back to the Boyle's law equation, you have P1 equals P2 V2. Okay, and of these 4 values, P1, V1, P2, V2, you are given 3 of them in the sample problem. You're given initial volume, initial pressure, final volume, and then you're asked to find the new pressure, or P2. So all you are really doing is using basic algebraic skills, rearranging the equation and solving for the variable that you do not have. Now there are 2 ways you could really do this. It really just boils down to a personal preference. Some people like to rearrange the equation first and then solve for the variable that they don't have, or others will like to go ahead and plug in all the information first and then rearrange. It really doesn't matter. As long as you do it correctly, you will get the same correct answer. What I always like to do is I like to rearrange the equation first and then start plugging in values. That's just my personal preference. So we're asked to find the new pressure, or P2. To isolate P2 here by itself, you need to divide this side by volume 2. And whatever you do to this side of the equation, you have to do to this side of the equation also. So when you do that, the V2's cancel out here. So what you're left with is P2, what we're trying to solve for, and then what we have left over here, P1, V1, all of that divided by volume 2. Now it's just a matter of plugging in all the values. Alright, P1, which is 1.5 atmospheres, multiplied by the initial volume, which is 5.6 liters. All that divided by volume 2, 4.8 liters. Do all that math, you get 1.75 atmospheres. That will round up to 1.8 atmospheres. Alright, now we'll move on to Charles' law, which is the relationship between volume and temperature. So if we increase the temperature of a gas, the kinetic molecular theory will state that the motion, or the kinetic energy of those particles, will also increase. So if the pressure of a gas is constant, the volume will increase. So that's how temperature and volume are related. So if temperature goes up, volume goes up. Here's another graphic to illustrate that. So the Kelvin temperature of the gas is directly related to volume. If one goes up, the other one goes up. If one goes down, the other one goes down. That's assuming that the pressure and the moles of the gas are constant. In this container, you have the initial temperature of 200 Kelvin, and the volume is 1 liter. If that temperature goes up to 400 Kelvin, the volume will also go up to 2 liters. So these are directly related. One goes up, the other one goes up also. One goes down, the other one goes down also. So this is the equation for Charles' law. The initial volume divided by the initial temperature is equal to the final volume divided by the final temperature. And just like in Boyle's law, a standard way to ask a question like this is you've given enough data to figure out 3 of the 4 of these values, and you need to solve for the 4th. And we'll go over an example of that here now. Okay, here's a pretty standard sample question that you see for a Charles' law question. A sample of nitrogen occupies a volume of 250 milliliters at 25 degrees Celsius. What volume will it occupy at 95 degrees Celsius? And there's one thing I need to point out right away, and it's something that always throws off students if they're not paying attention. That is these. When you're solving problems with Charles' law, the temperature must be in Kelvin, not Celsius. So you cannot plug in 25 degrees Celsius or 95 degrees Celsius and get the correct answer. A lot of people will just kind of gleam over the data in the question and just plug in temperature 1, temperature 2, and thinking that they're going to get the right answer. But if you aren't using the correct scale, you cannot get the correct answer. So you need to convert both of these. So for these, to convert Celsius to Kelvin, all you do is add 273 degrees to them. So for this one, that now becomes 298 Kelvin. And then this one here, we add 273 to that, 368 Kelvin. That's something that's very important to remember when you're doing Charles' law questions. You must use the Kelvin scale for temperature, not Fahrenheit, not Celsius. Alright, so now you have 3 of the 4 values that you need, and just like with any other gas law, you have all the variables that you need except for one. You need to rearrange the equations to solve for that unknown variable. So again, the initial starting equation for Charles' law, initial volume divided by the initial temperature equals the final volume divided by the final temperature. So now you're trying to find the volume, because it's asking what volume would it occupy. So it's asking for volume 2, so we need to rearrange everything to solve for this. Alright, by going ahead to plugging in the values, initial volume, V1, 250 milliliters, that's what you were given here in the question. Initial temperature is not 25 degrees Celsius, but 298 Kelvin. You have to use Kelvin, otherwise these equations don't work. V2 is what we're solving for, and then divided by the final temperature, not 95 degrees Celsius, but 368 Kelvin. So now you just rearrange this and solve for volume 2. To isolate volume 2 by itself, you would multiply this side of the equation by 368 Kelvin. And what you do to this side, you must do over here also. Multiply all that by 368 Kelvin. You have to do the same thing over here. Kelvin. And when we do so, these values cancel each other out. They're just left with V2. Is V2 over here. 368 Kelvin multiplied by 250 milliliters. That quantity divided by 298 Kelvin gives you a total of 308.7 milliliters. And depending on how specific that you need to get with your answers and significant figures, just by doing the math, you will get 308.7 milliliters. But if you are going by just the number of significant figures, you're only going to have 2 significant figures in this final answer, or you should only have 2 significant figures. So that answer will become 310 milliliters. There's only 2 significant figures in this answer, the 3 and the 1. Alright, now we'll talk about the relationship of temperature and pressure. It's also known as Gay-Lussac's law. Temperature, or the Kelvin temperature of a gas, doubles at a constant volume. The pressure will also double. So they are directly related. So here's a graphic that's given here. The temperature is 200 Kelvin, and the pressure is 1 atmosphere. If that temperature were to double up to 400 Kelvin, the pressure will also double. So there is a direct relationship between those two variables. And as that graphic again is a little bit bigger, a little bit clearer, doubling the temperature from 200 to 400 Kelvin will double the volume from 1 liter to 2. And here's the equation for Gay-Lussac's law. The initial pressure divided by the initial temperature is equal to the final pressure divided by the final temperature, assuming that the volume is constant. And just like the Charles law, just like Boyle's law, the way to ask this kind of question normally is to give you 3 of the 4 variables and ask you to find and solve for the 4th. Alright, now we'll talk about vapor pressure and the boiling point. When liquid molecules with sufficient energy break away from the surface of the liquid, they become a vapor. So in an open container, all of the liquid will eventually, at some point, evaporate. In a closed container, the vapor will accumulate and build and build and build and create a pressure called the vapor pressure. A liquid will exert its own vapor pressure at a given temperature, and it will boil when its vapor pressure becomes equal to the external pressure. Now we'll talk about the boiling point altitude and how they're related. But as you get higher in altitude, the atmospheric pressure will go down, and also the boiling point of water will become less than what it would be at sea level. At sea level, at 1 atmosphere, it's going to be 100 degrees Celsius. But the higher you go in elevation, that boiling point goes down. In a closed container, like a pressure cooker, the pressure is greater than 1 atmosphere, and also the water will boil at a higher temperature than 100 degrees Celsius. And here are some common examples. The normal sea level here, 760 millimeters of mercury, which is equal to 1 atmosphere. Water will boil at 100 degrees Celsius. The higher in elevation you get, the lower the air pressure gets. So let's say you're down here. So instead of being at 760 millimeters of mercury, down to say 270, the boiling point of water is now 70 degrees Celsius, not 100. And the opposite of this will be true also. If you get a higher pressure than the 1 atmosphere, say 2 atmospheres here, The boiling point for water is now 120 degrees Celsius. Now we'll talk about an equation called the combined gas law. The combined gas law will use pressure and volume and temperature relationships from the equations we just talked about. Charles' law, Boyle's law, Gay-Lussac's law, if combining all of them together in one equation. That's called the combined gas law. Here's the way it's represented. P1 times V1, all that divided by T1. So the initial pressure times the initial volume, all that divided by the initial temperature, will equal the final pressure times the final volume, all that divided by the final temperature. All this is the combination of the three equations we just talked about. Gay-Lussac's, Charles, and Boyle's. And just like any of the other equations we talked about, you may be given all these but one, and you need to solve for the one that's not given to you. Alright, now we'll move on to Avogadro's law. This shows a connection between volume and moles. In Avogadro's law, the volume of the gas is directly related to the number of moles of that gas. This is assuming that the pressure and temperature are constant. So the example that's given here in the graphic, if you have 1 mole of a gas, it occupies 1 liter. If the amount of moles goes up, the amount of volume will go up also. And the equation for Avogadro's law, the initial volume divided by the initial amount of the gas will equal the final volume divided by the final amount of moles of that gas. And following our pattern of all the other equations, you're usually given 3 of these values or enough data to solve for all 3, and you're asked to find the 4th. Alright, next we'll move on to something called STP, standard temperature and pressure. Now the volumes of gases can be compared at STP when they have either the same temperature, or they have the standard temperature of 273 Kelvin or 0 degrees Celsius, or if they have the same pressure, or if they have the standard pressure of 1 atmosphere. Now at the standard temperature and pressure, 1 mole of a gas occupies a volume of exactly 22.4 liters. So this value is called the molar volume. Again, these are equivalent values. So 22.4 liters is the same thing as 1 mole of a gas. And here are some ratios to compare. 1 mole of gas equals 22.4 liters. And depending on what unit you're trying to get rid of and what unit you're trying to find will determine which one of these will be on top, which one of these will be on the bottom. Alright, next we'll move on to a very important equation in chemistry called the ideal gas law. And the ideal gas law is the combination of 4 properties used to measure a gas: the pressure, the volume, the temperature, and the amounts, to give a single expression. And it's written as this: PV equals nRT. So pressure times volume will equal the amount of the gas times R, which is a constant, which we'll talk about next, times the temperature. If you take a chemistry class, you will see this equation quite often. Now, I mentioned how the value of R is a constant value, and here is what that number represents. And it really just depends on what unit you're using for pressure. If you're given pressures in atmospheres, you need to use this value: 0.0821 liters times atmospheres, all that over mole times Kelvin. If you're using millimeters of mercury, you need to use this value: 62.4 liters of millimeters of mercury, all that divided by mole times Kelvin. All the other units will be the same: liters, moles, Kelvin. And this is what I was referencing earlier in the chapter. You have to be very, very careful to use the correct units. If you're given a question and you're given millimeters of mercury, and you're asked to use this equation, and you use this value instead, not only will the values be completely wrong, but the units won't cancel out correctly. That's why these units are listed how they are. If you are given a measure of pressure in, say, torrs, but don't convert it to atmospheres or millimeters of mercury, you're going to get the wrong answer, and you can't use this equation properly. If you don't represent the volume in liters, you'll get the answer wrong. Or if you're not using moles correctly, or if you use Celsius and not Kelvin. These units are part of that identifier for that value. What happens quite often for students is they focus on the numerical value of the question and not the units. They just add on the units at the very end. But the unit is a part of that identifier for that value. If you're asked to find a measure of volume, and the final unit you come up with is grams, well, obviously you did something wrong. Gram is a measure of mass. For volume, it should be liter or milliliter. So the units should not be ignored. Units are a key part to any chemistry question answer. But again, the value for R in the ideal gas law is a constant value. You use either one of these, depending on what you are given in your question. And we'll go over an example of a question like that here now. Okay, here's a typical question when it comes to the ideal gas law problems. And we'll go over some common mistakes that people make when it comes to this equation also. Question: if I have 4 moles of a gas at a pressure of 5.6 atmospheres and a volume of 12 liters, what is the temperature? So just in this question, you already have all the information that you need to solve for the equation. So we'll start off with our generic equation. PV equals nRT. Alright, we have pressure, we have volume, we have N, number of moles, and then of course the R is a constant value. R will equal 0.0821 liters, atmospheres, all that over Kelvin times mole. Now this is the most common way to represent the value for R, that constant 0.821 liters, atmospheres, all that divided by Kelvin mole. There are other values, but this is the way that you will often see it represented. And this is important because you must use these correct units. You have to use liter and atmosphere and Kelvin and mole. A lot of times for chemistry classes, you're given questions just like this one that we're going over now, but you're given the pressure in torrs or in pascals or in millimeters of mercury. You must be able to convert all of those to the correct units, otherwise the answer you get will be wrong. You can't just plug in values from the question and what you think is temperature, what you think is moles, what you think is pressure, and expect to get the right answer. If you use the wrong units, these units won't cancel out. So a good indicator of if you're doing it right or not, if you're asked to solve temperature like we are in this question, if you come up with an answer as a measurement of volume, then you did something wrong. If you came up with a measurement for moles, that's obviously wrong. So always look at what you're given in your question and look at what you have to solve for. And then if you use the units correctly, they will cancel each other out. Alright, this question we need to solve for temperature. So we need to isolate temperature over here. To isolate temperature here, we need to divide this side of the equation by nR, so we can cancel out. And whatever you do to this side of an equation, you must do to this side of an equation. Divide that by nR, that by nR. So those will cancel each other out on this side. So what you're left with is T by itself, what we're looking for. And now you have PV over nR. And now it's a matter of plugging in the values and the units and seeing what you have left. So pressure, 5.6 atmospheres, times the volume, 12 liters. All that over N, which is 4 moles. And then the value for R, 0.0821. That's what you have. 67.2 for the top. At the bottom. 0.3284. So 67.2 divided by 0.3284. (204.6 Kelvin), and that would be your final answer. But again, the key problem that people have with the ideal gas law, even though it is pretty straightforward, PV equals nRT, you must use the proper units when you're using the value for R. If this question had the pressure in, say, torrs, you couldn't use this value because torrs and atmospheres would not cancel each other out as units. So make sure that you are using Kelvin temperature, you're using liters for volume, and you're using atmospheres when it comes to the pressure. when using this value. Alright, now we'll talk about the gas laws and chemical reactions. Now, gases are involved as reactants and products in countless chemical reactions. And typically the information that's given for a gas is its pressure, volume, and temperature. And you can use the ideal gas law to determine the moles of the gas in the reaction, as if you're given the number of moles for one of them, and the moles of the other substance using the mole-mole ratio. Alright, next we'll move on to what's called partial pressure, or also known as Dalton's law. And the image that you see here is the heart sending oxygen both to the cells of the body and also receiving oxygen from the tiny air sacs in the lungs called the alveoli. Alright, all cells in our body are constantly producing carbon dioxide and have the constant use and need for oxygen. So both gases are moving in and out of the lungs at the same time, all based on simple diffusion and what's called partial pressure. And that will determine how much and how quickly oxygen will diffuse into the blood to be delivered to body tissues, and how quickly carbon dioxide can be eliminated from the lungs to be breathed out. Now, partial pressure is just the pressure that a gas would exert on a container if it were in a container by itself. So it is the pressure of that part of that gas. And here's what I mean by that. Let's say you have a container here. It's filled with argon and helium. Let's say that the total pressure in this entire container is 6 atmospheres. If you were to look at just the pressure of just the helium part, that's going to be measured at 2 atmospheres in this example. So the partial pressure of helium is 2 atmospheres. The pressure of the argon by itself, just the argon, would be 4 atmospheres. Right, so if the total pressure of both of those together is 6 atmospheres, just a portion of helium is 2 atmospheres, just a portion of argon would be 4. So that's what the partial pressure is, just focusing on just one component of the overall total. And that leads us to Dalton's law of partial pressures. This indicates that the overall pressure of a gas is indicated by the total number of gas particles and not on the types of the particle. The total pressure exerted by a gas of a mixture is the sum of all the partial pressures. It's like we saw on the last slide. The total container was 6 atmospheres. That was the total of the pressure of the helium plus the pressure of the argon and so on. So that's what this equation represents. The total pressure equal to the pressure of the first part plus the pressure of the second part and so on. So helium would be, say, the first pressure, argon would be the second pressure. So you keep adding all the individual components of that mixtures of gas to get the overall total pressure.